Thank you. Okay, this is my token World War II cannon or gun, because I'm going to be showing you cannons from earlier shipwrecks, but the treatment processes I'm talking about are very likely to be applied to these weapons, should they ever be recovered. Okay, generally on a shipwreck site that I visit most of the time, cannons are lying on the seabed, like this one in the middle. And as Vicky has mentioned, we do corrosion measurements on shipwrecks and their objects on these shipwrecks. And here we have some of the equipment we use. We have underwater meters. We drill into the concretion layer, which is the corrosion products and cement-like materials that have formed on the outside of these objects. We drill through the concretion. We come to the metal, the drill stops at that point, and then we take a pH probe and insert that. We can get the pH underneath the concretion. Seawater is about 8.2, which is slightly alkaline. Underneath the concretion is quite acid, so we can measure that. We then take our corrosion measurements using a platinum probe, and once we've done all this, gathered this information, we can work out what's happening to that object, whether how actively it's corroding or not. We then plug the hole, because on a principle we don't want more seawater going in there. It's a very small hole in the scheme of things, and especially when you're drilling a shipwreck, it's not going to have a huge impact. We can also fit anodes to these objects, and if we do, we can stabilize them underwater and actually begin the treatment process underwater. I can't imagine it will be something we'll do to a cannon on a shipwreck, like the Fujikawa Maru, for example, because for one thing, it may be in direct contact with the ship itself. If we install an anode, it will also be trying to protect the ship. The anode will probably last half an hour or something like that because it corrodes away. And of course, ultimately, the shipwreck will collapse anyway, so why are we trying to preserve the gun on the deck? With recovery, excuse me, with recovery, usually we go to a shipwreck site, and part of the plan is to recover a cannon. And when you do so, you have to excavate around it, and in that process you might find other things, and that's what usually happens if it's on sediment or in sand. And that's what that little pocket watch is there that was found when we were excavating around this cannon. In fact, Bill Jeffrey found that many years ago. Of course, when you recover a cannon, it's got concretion on it. That concretion also sticks the object to the seabed. It's like a truck has poured cement or concrete over the top, and actually bonds to the seabed. And the weakest interface is between the cannon surface and the concretion. And usually when you free the cannon, you leave that concretion behind and you have a gap. And that's why you can see in this smaller gun underneath, you can actually see the gun surface itself. We can use lift bags. It can be a bit a rough situation, as you can see with this gun from the Cumberland. But it's better to actually moor your vessel over the side if possible and recover it that way with a winch. Once we've got the cannon up, it's a concreted object. That concretion actually forms a good barrier between the atmosphere and, in other words, a buffer between the wet environment and the dry environment. But it will dry out, and if you leave the cannon to dry, it will start corroding, and then when you do your treatment process, the actual thing will start to fall apart. So we have to keep it wet, and the simplest way to do that is to simply wrap it up. Put some wet material around, some burlap, saturated with seawater, seal it up in plastic, and then tape it all up, make sure it stays wet. Once we get back to our lab, then it can go into a tank for treatment. This is the good usual tank we have, so you can treat an anchor and 2 cannon, or maybe 4 cannon if you so wish. This tank contains caustic soda solution, a 2% solution. It's enough to burn your skin and blind you if you're not careful, so you have to be careful when using this product. But once you put your object, an iron object, into that solution, it stops corroding, and that's why we use it. Removing the concretion is a tricky process. The idea is really to crack the concretion so that you can actually lift that material off, and when you do, you can see in the lower right-hand corner, if you lift the pieces off, you have the cannon underneath. And the thing about, say, cast iron cannon in particular, even though the metal is corroded, because it contains carbon in the form of graphite, that material is inert, and being so, it doesn't corrode away. So essentially, you have a solid or complete object underneath. It's lost weight because it's corroded, but essentially the original object is there. And the beauty is it retains all the markings, the stamps, whatever's on the gun. Got to be a little bit careful because you can dislodge the raised portions like the mouldings and the vent and so on and so on. So you have to be careful how you do it. And of course, concretion not only goes on the outside and forms on the outside, but also form on the inside. So if necessary, when it's blocked like this, we have to actually core it out. And this is the process. Essentially, we use a drilling machine, and we have to take a section of core out of this concretion, and then we back it out, put an extension rod on, and go back in again until you get down the back of the gun. And some of these guns are almost 3 meters long, so it's quite a long process. This one here is a fairly short one, the one I'm working on myself there. And as you can see, I'm lifting out the concretion. The concretion is not always solid in the bore. Sometimes, if you're lucky, you'll pick up the cannonball. In this right-hand photo, you can see there's the cannonball. There's some of the wadding which was used to hold the ball in place and stop it rolling out of the gun. Because there's no point having guns on board if they're not ready to fire, because you need to use them straight away. Sometimes, if you're lucky, you find the wooden tampion plug in the end of the gun. So you remove a bit of concretion and the wooden plug is still there. That's great because it means you don't have to remove the concretion from the ball, because essentially it hasn't formed inside. So here we are, we're cutting around the tampion with a blade just to free it. And then once you look inside with a flashlight, you can see what's inside. And we have the wadding, which in this case is made of cordage or rope, bound up into a tight bundle to hold the ball in place. And we have an instrument here called a worm, which we replicated, and we were able to extract that wadding. And when we did, we could see the cannonball. We lifted up the back of the gun and the ball rolled out. And this is from 1712. Obviously, there's the contents of the cannon. They're not all in that position. The tampion is at the very front, of course. And then you have the wadding, the ball, the wadding, and then the powder bag, and that's all that's left. The other thing is we always keep a hose running nearby, because when you open up a cannon like that, all the oxygen that's in there has been consumed. When it gets the oxygen from the air, you can actually get spontaneous combustion taking place from the rapid corrosion of the reduced environment in there. So the wadding can start smouldering, for example. Now, if the powder were viable in the gun, then it's going to empty itself pretty quickly. But so far, we've never found a gun, and we've tested gunpowder we removed from grenades and cannons, and it's never been viable, so touch wood. Next thing we have to do, once it's deconcreted, sit it on a cradle, insulated from the actual cradle itself, with some rubber, and then we set it between some anode sheets, which are positive sheets, and then we have the gun itself, which is the negative side of this process. So we set it up in a tank with the caustic soda solution, as you can see here. Besides the sheet anodes, which go either side of the gun, we also have a bore anode, which essentially is a rod, and that rod is also acting like an anode internally. It's insulated from the bore, and that's what happens here. Essentially, in that solution, the salt which is in the gun, the chloride ions, are negatively charged. When we pass a current through this system, those negatively charged ions migrate into the solution towards the positive anode sheets on the outside, or the rod on the inside. And that's how we get the chloride out. Also, the electrolytic reduction process reduces the volume of the corrosion products, so it makes the cannon more porous, and also that encourages the solution to go in and the salts to come out. To treat a cannon that's been under the sea for about 300 years, you're looking about 1 year of treatment per century to stabilize it. So on average, about 3 years. But if you consider it's been under the sea for 300, it's not a bad time. Okay, this is the process of lowering into the tank. And you can see these are the transformers that we use to connect to the guns. The gun cannot just sit on the cradle all the time. It has to be moved, because if you don't move it, those areas trap salt. And that's a consequence of this cannon here, which was actually one from Captain Cook's Endeavour which was treated in earlier times before they thoroughly thought the process through, and consequently had corrosion activity something like 30 years after it actually treated. So it had to be retreated. Of course, what we have to do as the salt's going into the solution, we have to take a sample, we analyse how much salt is in that solution, and gradually, of course, it increases. Eventually, the amount of salt in the object is the same in the solution. No more salt's going to come out, so you have to renew the solution and start the process again. And you may do this 3 or 4 times, depending on how long it takes. And eventually, when you've got rid of all the salt, when it's all gone out into the solution, we have to soak the gun in a distilled or deionized water. We exclude oxygen by putting a filmed oil on the surface and put some sodium sulfate, which scavenges the oxygen from that solution. And then we can just leave it there to soak, because the caustic soda that's in that gun, if we take it directly from the solution, it will form into a carbonate and effloresce on the surface and form a white film, which is undesirable anyway. Just to confirm, we've removed all the salt. What we do is drill into the gun in 3 places, towards the muzzle and the rear and the centre, and then we can analyse those samples we've taken just to confirm the amount of salt. There is very little residual salt. We accept around about 50 parts per million. Next job, once you've dried those guns, you can dry them after that. And then we apply a corrosion inhibitor, which is a tannin-based product. You've probably seen these. You apply it to rusted surfaces and it turns black and stabilises the metal. And then after that, once we've sprayed it inside the bore and coated the outside, then we can immerse the whole thing into wax. And so we have a big tank of molten wax, and we submerge the gun. And the reason we do this is because that corroded outer layer is really quite soft. There's a residual metal core in the gun, but the corroded outer surface is graphitized. It's almost like pencil lead, if you like, and you can scrape it almost with your nails. And we need to consolidate it. And the idea is by submerging in the wax, it actually penetrates into the porous surface, and before it obviously solidifies, we recover it, and that wax cools and actually strengthens the gun surface itself. The final thing we do then is coat shellac on the wax. Shellac is compatible with the wax, and that just makes a smooth, non-sort of sticky surface that is good for cleaning if you're getting dust off and so on. And why do we do it? Well, if you don't do it, this is what happens. All that graphitized outer layer with all the information, all the markings, all the things you need to record, all the dimensions, will just simply fall away. And this is what has happened to a lot of cannon in the past. I'm sure you've seen them. Everybody wants to drag the cannon out and put it on display along the shoreline somewhere, or in their garden, if they're allowed to in the early days, and gradually they just fall to pieces. So there's a couple of examples there of that, and this is another cannon that we've treated. And of course, if you want to, then you can do a bit of research, find out what the gun carriage looks like, and then put it on the gun carriage. And really, that's the process. I'm sorry if it sounds a little quick, but limited time to talk. And the last thing I'd like to say is, of course, once you've done conservation on any object, there are certain requirements, or ideal requirements, for storage or display. And this is just by way of an example of the sorts of conditions we would try to have for an object in a museum. Realistically, of course, there are a lot of things made of different materials on display in a museum, and everything has its own environmental requirements. But you can't supply the environmental requirements for everybody, including the people that come to visit the museum. So essentially, unless you want to put it in a display case with specific controls, buffers or whatever to keep it in a particular environment, then usually it's a compromise. But these objects, once they're treated, impregnated with wax, they're moisture resistant. We don't put them outside because the conditions are too harsh. You can't watch it, you can't stop people hitting it with something and chipping it and causing problems. So essentially, that's the process for the treatment of guns. If we had to do this with a World War II gun, then it would be pretty much the same process. Thank you.